All right, welcome back, everyone. This is it, the final explainer in our Back to the Roots series. We have journeyed from the very spark of an idea all the way to the physical hardware. But there's still one big mystery left to solve. So, we left off with this, right? We know that in the computer's world, 1 plus 1 equals 10. But how? I mean, what is that actual thing buried deep inside the silicon that takes two ones and somehow almost magically spits out a 1 and a 0? Well, today we're going to find that thing. Okay, let's get right into it. The answer to our mystery is something called logic gates. The best way to think about them? They're the absolute fundamental Lego blocks of our entire digital world. Or, if you like, think of them as the individual nerve cells of the computer's brain. They're the simplest, smallest, yet most ridiculously powerful little components inside every single processor. Now, here's the really wild part. Every single complex decision your computer makes, I'm talking from adding numbers to rendering a video game, is all built from just 3 incredibly simple little rulers. So, let's meet them. First up, we have the AND gate. I always picture this one as a really strict guard, the kind with a clipboard at some super exclusive club. It has a very simple but very, very rigid set of rules. So the rule for the AND gate is this. It will only give you a 1 or an ON signal if input A and input B are both 1. If even one of them is a 0, nope, the output is 0. Think about it like a simple light circuit with 2 switches in a row. To get that bulb to light up, you've got to flip both switches. One's not going to cut it. And this right here, this is what we call a truth table. It basically shows you every possible combo. And notice, the only time we get that 1 in the output column is when both inputs are 1. It's that simple, totally predictable, and incredibly powerful. All right, on to our next ruler, the OR gate. Now, if the AND gate was that strict guard, the OR gate is his easygoing buddy. This one is way more relaxed. Its rule is just as simple. It will output a 1 if input A or input B is a 1. It doesn't care if it's just one of them or if both of them are on. The circuit metaphor here is perfect. Imagine 2 switches side by side, in parallel. You can flip either switch or both, and the electricity has a path. The bulb lights up no matter what. And yep, the truth table totally backs this up. See? The only way to get a 0 out of this thing is if both inputs are 0. Any little glimmer of a 1 on the input side, and you're getting a 1 on the output side. And our third and final ruler is the simplest of them all, the NOT gate. This one doesn't make any decisions. It just does one thing and one thing only. It inverts. It just flips whatever you give it. Yeah, this one's a little different. It only has one input. You give it a 0, it spits out a 1. You give it a 1, it spits out a 0. That's its entire job, to be the ultimate contrarian. It's a simple inverter. Okay, so we have a strict guard, an easygoing guard, and an inverter. And you're probably thinking, that's it? That seems way too simple. Well, this is where the real magic happens. It's all about how we combine them. So let's go back to our big mystery. 1 plus 1 equals 10. We solved this puzzle using a little circuit called a half adder. Now, for the first digit of our answer, the 0, we need a special kind of logic. We need a gate that's true if either input is 1, but not if both are. And believe it or not, we can build that by cleverly combining our 3 rulers. We call this an XOR gate. So when we feed our 2 1s into it, 1 XOR 1 equals 0. Boom, that's our sum digit. And the other digit, the carry digit, that's just our old friend the AND gate. It takes the same 2 1s, and 1 and 1 equals 1. And there you have it, a 1 and a 0. 10. Did you catch what just happened? I mean, really think about it. We took a couple of these super simple, almost dumb Lego blocks, and we built a calculator, a real working circuit that can do math. That is the fundamental magic of all of this. So, if we can build a tiny calculator with just 2 of these gates, what happens when we start using more? A lot more? Well, this is how we scale from a couple of Legos into a modern processor. And when I say a lot more, how many are we talking? Thousands? Millions? Nope. Try billions with a B. The CPU in your phone or your computer has billions of these tiny logic gates all working together, flipping on and off, making trillions of simple decisions every single second. It's just mind-boggling. And this all creates this beautiful pyramid of complexity. At the very bottom, you've got transistors, the physical on-off switches. We arrange those to build our logic gates, our Legos. Then you snap those Legos together to make useful circuits, like the adder we just designed. You combine those circuits into bigger components, like the arithmetic logic unit, or ALU, which is kind of the mathematical heart of the processor. And finally, all of that together becomes a CPU, the brain of the computer. Each layer is built from the simple genius of the one below it. And, just like that, our journey back to the roots is complete. We started with just an idea, and we've drilled all the way down to the nerve cells of the digital brain. We now understand the absolute foundation of all modern technology. Here's the really cool part. By following this all the way through, you now have a foundational understanding of how this stuff works that, honestly, very few people in the world possess. You've seen the basic building blocks of our entire digital lives. I really hope you've enjoyed this deep dive to the roots of the tech tree. But you should get ready, because our next series is just around the corner. We're going to climb up from the roots and step out onto one of the most important branches. We're going to learn how to code and work with Git and GitHub, the absolute essential tools for every developer out there. Thank you, as always, for joining me. Until we start that next chapter, I'll leave you with this to chew on. If these tiny logic gates are the brain cells, and now we know how they think, what amazing things are we going to teach them to do next?